Aloha, my name is Bridget Smith-Konter, and the title of this talk is Geodetic Imaging of the 2018 Kilauea Volcano Eruption and Earthquake Sequence. Before I begin though, I'd just like to acknowledge several students and colleagues at both the University of Hawaii at Manoa and Scripps Institution of Oceanography that contributed to this work, as well as the efforts of many collaborators from the USGS and the Hawaiian Volcano Observatory. So I will begin with one really important statement that I will attempt to map out over the next few minutes, and that is that the 2018 Kilauea volcano eruption provided an unprecedented opportunity to geodetically image volcanic and tectonic deformation like what you're seeing here in this image, and to do it in near real time. It was really an exceptional chance to rapidly obtain and process and share geodetic data with the scientific community, as well as the public. And as it turned out, as we all know, this event not only had temporal stamina, but spatial complexity as well, with 3 events or processes occurring nearly simultaneously. So geodetic observations like GPS or InSAR is Interferometric Synthetic Aperture Radar. These offer a unique perspective of surface deformation spanning multiple temporal and spatial scales. So this talk will primarily feature InSAR results like those seen here on the right. However, it is important to note that GPS and InSAR data are not only complementary, but when integrated, they can be a very powerful tool for exploring both temporal and spatial deformation patterns. So Kilauea has a network of permanent GPS receivers that measure ground displacement in the northeast and vertical directions, and these can record data up to every 30 seconds, thus providing excellent temporal resolution. InSAR data, which I will explain a bit better detail next, measure deformation observed by Earth orbiting satellites and is largely sensitive to vertical motion. So as a really simple guide, blue colors in most of the maps I'll be showing will indicate subsidence, and red colors will indicate uplift. So here I'd like to briefly illustrate 3 significant events that were beautifully observed by both GPS and InSAR. The first of these is the May 1st dike intrusion that extended from Pu'uo'o to Leilani Estates. Both the GPS and the InSAR data clearly show the deformation caused by the newly intruded dike into the lower rift zone and the deflation of the active portion uprift of Pu'uo'o. In the GPS plot, the light blue dots representing a baseline length change between 2 different GPS stations here, stations NUPM to PG2R, and together these show deflation of the old active portion of the magma storage and transport system uprift of Pu'uo'o. Now, east of Pu'uo'o, or the red dots shown in the plot here, these show stations responding to the intrusion of the new dike down rift and the subsequent contraction as the initial pressure is released through propagation of the dike and the eventual eruption at Leilani Estates. The second event I'd like to mention is the magnitude 6.9 shallow thrust earthquake on May 4th, where the InSAR data show an obvious and large seaward and downward displacement of the south flank. Gray dots highlight the stations recording the large ground motion generated by fault slip during this magnitude 6.9 earthquake. And then the last event I'd like to point out is the remarkable deformation or deflation at Kilauea's summit. So both near and far field subsidence is evident in the InSAR data as these large volumes of magma were withdrawn from the summit. But over in the GPS plot, the gold dots, whose stations are near the summit, respond very weakly to the dike event in late April, but with increasing deformation only a few days later when large volumes of magma began withdrawing from the summit. So a quick summary of InSAR, or Interferometric SAR. InSAR measures changes in land surface through high density measurements over large areas that use radar signals from Earth orbiting satellites. And we use this technique to measure changes in land surface altitude at really high degrees of measurement resolution and spatial detail. So SAR imagery is produced by reflecting radar signals off of a target area and then measuring the two-way travel time back to the satellite. The SAR interferometry technique uses two SAR images of the same area acquired at two different times and then interferes or differences them, resulting in maps that we then call interferograms. So in short, interferograms show ground surface displacement, or what we call range change, between the two time periods that appear as a series of interference fringes. We also call this a wrapped signal. And each set of fringes represents a quantity of displacement, say 3 centimeters, in the satellite's line of sight direction that is dependent on the satellite's radar wavelength. So our group primarily used SAR data from the Sentinel-1 satellite to monitor the 2018 Kilauea eruption. The C-band Sentinel-1 satellites, which are operated by the European Space Agency, or ESA, provided a special 3-day coverage. This equates to really a 6-day repeat orbit of the 2018 Kilauea eruption. And the Sentinel radar is right-looking. So this means that when we have ascending tracks, these are tracks that fly from the south to the north, and they look to the east, whereas descending tracks fly from the north to the south, and they actually look to the west. And so the plot on the right here shows the many Sentinel SAR acquisitions of Kilauea throughout the 2018 summer, and also the suite of combined image pairs that one can use to develop a really large comprehensive suite of InSAR data. I should note that all of the Sentinel SAR data are freely available on the Sentinel Data Hub at the website provided here. And during the 2018 eruption, data were typically available to researchers for download within 6 hours of acquisition by ESA. So here I will be showing two forms of InSAR data products. First one that we're looking at here is what we call a wrapped phase map, and this spans two dates, April 20th to May 2nd. And this image really nicely captures the dike intrusion that began on May 1st that extended from Pu'uo'o to Leilani Estates. Now here each rainbow fringe represents 2.8 centimeters of surface displacement as viewed from the satellite radar. So any speckled patterns that you see in this image are largely attributed to atmospheric or topographic noise, and in this case even sometimes ash. But overall the dominant signal here is a strong pattern of continuous fringes that emanate from the east rift zone, and the ground motion can be interpreted by counting the number of fringes inward toward the center and then multiplying by 2.8 centimeters. So the 7 fringes that maybe you can make out here are roughly equivalent to about 200 millimeters of ground motion. Now, on the right side here is the same data, just shown in a different form. This is what we call a radar line of sight displacement map. And this is of the same event where the fringe patterns that you see on the left are now unwrapped and interpolated as displacement away from or towards the satellite. Now the Sentinel radar is mostly sensitive to vertical motion, so red colors typically translate to uplift or displacement toward the radar, and blue colors typically represent subsidence or a displacement away from the radar. However, because Sentinel is side-looking, it is also sensitive to east-west motion. So, however, the sign of this signal, which will be positive or negative, will depend on the flight direction. So if the flight track is ascending, like the one that's shown here, we'll see red colors that indicate motion toward the satellite or to the west. Blue colors, in this case, indicate motion away or to the east. Now, if this were a descending flight direction image, then these colors would be reversed. So here we see nearly 200 millimeters of displacement away from the satellite in blue, or subsidence due to deflation uprift of Pu'uo'o. We also see several tens of millimeters of displacement toward the satellite, or uplift, that are really due to the newly intruded dike into the lower rift zone. So I wanted to briefly demonstrate the dependency of line-of-sight displacement on the flight path direction, where here we compare line-of-sight displacement maps for a sequential ascending-descending pair of images. Now on the left is the line of sight displacement for the ascending interferogram that we saw on the previous slide, spanning April 20th to May 2nd. But now here on the right, I've included a descending interferogram spanning April 23rd to May 5th. Now in this case, we're seeing a slightly different pattern between the two maps, and this is due to rapid changes in deformation, but also due to a change in observation geometry, where the descending line of sight displacements that we see on the left, or excuse me, on the right, are now showing red colors, now as uplift or eastward motion, and blue colors are shown as subsidence or westward motion. So for the map on the right, intrusion-induced subsidence is still evident along the east drift zone, but now two new processes are also captured in this unique map. The first one that you might see is a small but emerging circular subsidence signal, and this is occurring at the summit. And the second is a large swath of increased motion toward the satellite that shows up as deep reds, and this is hugging the coastline of the south flank. This interesting signal is actually due to the southeastward or oceanward slip from the magnitude 6.9 earthquake that occurred on May 4th. So this is a good time to deviate for one brief moment to provide a few words on the magnitude 6.9 earthquake that occurred on May 4th, 2018. This was the largest regional event in 43 years, which displaced a substantial section of Kilauea's south flank, estimated between 1 to 3 meters seaward. Its epicenter was just offshore, and this earthquake was a thrust event with a preliminary focal depth of about 2 kilometers on a plane dipping 20 degrees inland. However, subsequent modeling from various groups infer that the dip of the fault plane is somewhere between 2 and 20 degrees at depths ranging from 2 to 8 kilometers, spanning really a group of detachment faults above the basal décollement between Kilauea and the old ocean floor. Now, a reason for the large uncertainty in the earthquake source can be attributed to the offshore location of this event. It's just that the deformation primarily occurred offshore, so it's really harder to constrain the earthquake source. We performed a joint GPS and InSAR inversion of the event to develop a high-resolution slip model. This can be seen on the bottom left here. And to the right, in the middle section of this slide, are our model surface deformation estimates. As you can see, the descending line of sight displacement map from this event was largely offshore, hence the lack of signal seen in the actual interferogram, which is shown right above it. So when projected into north, south, east, west, and vertical components, we can estimate surface slip to be close to about a meter in the southward direction, about a half a meter in the eastward direction, and then a little over about 0.3 meters of subsidence on the landward side of this thrust. Now, of course, we know that the action did not stop at the May 4th earthquake, but little did we know at the time that we were about to embark upon multiple months of InSAR processing. We officially processed and distributed online in near real time our first interferogram on May 2nd, and continued this approach for the next 7 months with our last interferogram posted online on December 7th, 2018. These data are available on the Pacific GPS Facility website that's shown up in the top right corner. Each interferogram was processed with open source software GMT SAR and was posted on the web within 4 to 6 hours after the data were made available by ESA and then processed by our group. On our website, over 60 raw interferograms and line of sight displacement maps are available. And these data do contain contributions of atmospheric and topographic noise, both of which were later treated for in our InSAR time series algorithm that I'll talk about next. So to make an InSAR time series, we use 170 interferograms spanning February 1st to September 15th, 2018, a period needed to fully bracket the entire eruption. Here we see a subset of these time series from April 4th to June. And I'm going to omit a lot of details that went into the construction of our InSAR time series, but an important thing to note is that we utilize the GPS data spanning Kilauea to correct for possible phase unwrapping ambiguities and atmospheric delays at longer length scales. So here is a time series animation spanning March to September 2018. The time step is noted in the upper right corner, where the last 4 digits represent the month and the day. We begin with relative quiescence for the month of March, and only at the end of April we begin to see the collapse of Pu'uo'o, followed by the May 1st dike intrusion, and then sprawling deformation along the south flank region from the May 4th earthquake. And this is followed by really just continuous deflation of Kilauea's summit region over the next 2 months as large volumes of magma are withdrawn. So from the Sentinel InSAR time series, we can then extract deformation profiles through time as we see here. This is a plot across the transect marked BB prime in the map that goes across the East Rift Zone, where displacement across the rift is colored in time with displacement in May in cyan, June is green, July is yellows to oranges, and August is red. And we can broaden this analysis to inspect deformation along the lower East Rift Zone, shown in the bottom plot, as well as at the summit, shown at the top plot. Now, Kilauea's summit time series reveals remarkable deformation within the summit crater as large volumes of magma were withdrawn. However, the Sentinel InSAR signal was significantly decorrelated in this region due to the collapse and deepening of the crater walls and interior. So, however, at distances exceeding 3 kilometers from the summit crater, the Sentinel InSAR signal reveals about 0.5 meters of broad far-field deformation. But inside the crater, LiDAR and UAV data reveal about 600 meters of subsidence at Halemaumau, and roughly 2 meters of subsidence just outside the crater, which is roughly consistent with the InSAR data that we see at this distance. So if we're looking for ways to measure the mass volume loss at the summit, we can start with the LiDAR data measurements of elevation difference, which suggest about 0.8 cubic kilometers of mass volume decrease. And then our next step is to ask what additional contributions to this estimate can be made from the InSAR data. So we next utilize the InSAR time series data as well as the GPS data to estimate the mass volume change spanning Kilauea's entire south flank. Here we perform a linear least squares inversion of the total deformation field from late April to mid-September to solve for the source volume change using multiple distributed sources at depth beneath Kilauea. Our best fitting model required a cumulative summit plus East Rift Zone volume decrease of about 0.25 cubic kilometers. Now, while this is a fairly small value, it's important to remember that this is based on data outside of Halemaumau, where most of the significant deformation occurred. So what we're really seeing is the contribution of mass volume change in the mid to far field range of Kilauea's summit. So one of the big questions about this eruption was whether or not the magma that contributed to the deflation at the summit was equivalent to that was erupted at the lower East Rift Zone. So we can ask, first of all, what was the total volume loss at the summit, and we can derive an estimate based on the source inversion volume change that we derived from GPS and InSAR, as well as the volume change from the LiDAR UAV data inside Halemaumau. And the combination of those two is roughly 1.07 cubic kilometers. Now this compares nicely to the estimates of Anderson et al. 2019, where they estimated anywhere from 11 to 33% of Kilauea's shallow magma reservoir was evacuated by the end of the eruption. And these numbers basically boil down to a summit volume loss of about 0.2 to about 2 cubic kilometers. So then we ask, how does this compare to the volume erupted along the lower East Rift Zone? Effusion rates from fissure 8 produced anywhere from 0.8 to 1 cubic kilometers of lava. And then we still don't quite know the full volume of erupted lava along the East Rift Zone or the submarine contribution. So to conclude, I'd just like to reiterate how unprecedented this opportunity was to geodetically image the 2018 Kilauea volcano eruption in near real time via 3 major deformation processes that took place over a span of 3 months. And of course, the relaxation processes in response to these events lasted much longer. To observe the full range of this ensemble event, 7 months of quasi-continuous InSAR data were processed and rapidly distributed to the scientific community. And in addition to the many other geophysical tools used to investigate this event, our group developed an InSAR time series using over 170 interferograms. And as a final note, I'd just like to say that the continual near real-time geodetic observations spanning this eruption event in 2018 provided an exceptional test bed for rapid hazard response, particularly relevant for remote regions. So thanks to this unique opportunity, we are now even better prepared to successfully integrate dense spatiotemporal geodetic data sets for things like post-earthquake and of course post-eruption rapid response. Thanks.